Hello, friend. Come closer for a moment. Rest where you are. Tonight we're going to talk about something strange, something that happens when you try to measure the universe too carefully. Imagine holding a ruler in your hands. You divide it in half, then half again, and again. It seems like you could do this forever, drilling down into smaller and smaller distances, peeling back layer after layer of reality. But you can't. There is a place where the ruler stops making sense, where measurement itself forgets how to work. That place is real. It has a name. And once you see it, you'll never think about space the same way again. Before we begin this quiet journey together, a small invitation. If you find comfort in these slow drifts through science, you might like to stay a while. You can gently tap the like button if this feels like home. Subscribe if you'd like more stories told softly in the night. And ring the little bell not for noise, but so the next quiet evening can find you again when you need it. No pressure, just a whisper in case you'd like to return. Now, let's drift. There once was a physicist named Max Planck. The year was 1899. The world was on the edge of a new century, and scientists believed they had nearly solved everything. Physics seemed complete. The universe, they thought, was just a very large clock, predictable, mechanical, eternal. Planck was studying something simple, the way hot objects glow. Heated metal, glowing coals, the sun itself. He was trying to understand why a piece of iron, when heated, shifts from red to orange to white. What he found broke the universe. He discovered that energy does not flow smoothly like water. It comes in packets, little indivisible chunks, quanta. This was strange enough, but in the mathematics of his discovery, Planck noticed something even stranger. He combined three numbers, three constants that describe the universe: the speed of light, the gravitational constant, and his own new quantum constant. When he wove them together, they formed something unexpected: a length, the smallest length that could mean anything at all, 1.6 times 10 to the negative 35 meters. It's hard to picture something that small. Scientists suggest that if you could somehow shrink yourself down past atoms, past electrons, past quarks, you would eventually reach a point where space itself stops being space. At least space as we know it. The Planck length is not just small, it is the edge. The boundary where the rules we've written for reality start to whisper, "I don't know what happens here." Planck had no idea what he'd found. He thought he was just creating a convenient system of measurement, a universal ruler that any intelligent being, human or alien, would calculate the same way. He was right about that, but he was also accidentally pointing at the strangest frontier in all of physics. Let's pause here and feel the scale for a moment. A proton, the tiny nucleus of a hydrogen atom, is about 100 million trillion times larger than the Planck length. If you scaled a proton up to the size of the observable universe, the Planck length would be roughly the distance from Tokyo to Chicago, a 14-hour flight, long to us, utterly invisible to the cosmos. And yet, scientists believe that at this scale, this unimaginably small scale, everything changes. The smooth fabric of space and time, the stage on which all events unfold, becomes something else. It wrinkles, it tears, it bubbles, it stops being a fabric at all. Some say it becomes a foam. Others say it dissolves into vibrating strings. Still others suggest that space and time themselves are illusions that only make sense when you step back far enough. Planck didn't know any of this. He published his paper quietly. He moved on. It would be decades before anyone understood what his little calculation meant. Before Einstein would bend space-time with gravity. Before Heisenberg would shatter certainty with his uncertainty principle. Before Wheeler would imagine space-time as a churning quantum foam. But Planck had opened a door to the smallest room in existence, a room where reality as we understand it becomes strange. Why does this happen? Why can't we just keep measuring smaller and smaller forever? It's not a limitation of our tools. It's not that we need better microscopes or more powerful telescopes. It's something deeper. It's that the very concepts we use to describe reality, distance, duration, position, start to lose their meaning. They become blurry, undefined, like trying to ask what happened before time began. The question itself stops making sense. Tonight, we're going to walk toward that edge together, slowly, gently. We'll meet the scientists who tried to map this strange terrain. We'll learn about the forces that unify there, the strings that might vibrate there, the black holes that might form there. We'll visit the first fraction of a second after the Big Bang, when the entire universe was smaller than the Planck length. You don't need to understand everything. That's not the point. The point is to drift, to feel the immensity and the smallness at the same time, to rest in the wonder of a universe that is at its deepest level still unknown. So, breathe, settle in, let your thoughts slow. The universe is about to become very, very small. In 1899, Planck combined three constants and found a length. But he found more than that. He found a time, the Planck time, the smallest duration that can be meaningfully discussed, 10 to the negative 43 seconds. In that sliver of existence light, the fastest thing we know travels exactly one Planck length. It's as if the universe has a clock ticking faster than anything we can imagine, and that tick is the Planck time. Nothing happens faster. Or rather, if something did, we'd have no way to describe it, no equation to hold it, no language to speak it. And there's a mass, too. The Planck mass, about 20 micrograms. Heavier than a grain of sand, but packed into a space the size of the Planck length. If you somehow concentrated that much mass into that tiny point, scientists suggest you'd create a black hole, the smallest possible black hole, a quantum black hole that would evaporate almost instantly in a burst of radiation. These three quantities, length, time, mass, form a kind of natural boundary, a set of cosmic limits written into the fabric of existence. Planck didn't set them, the universe did. He just noticed them the way you might notice the horizon line on a clear day. But here's the beautiful part, the mysterious part. These numbers aren't arbitrary. They don't depend on human choices on the length of a king's foot or the swing of a pendulum. They emerge purely from nature, from the speed of light, which is the same everywhere, from gravity, which pulls on everything, from the quantum, which hums beneath all matter. Any civilization anywhere in the universe would calculate these same values. They are universal, written in the stars, hidden in the equations. It's as if the universe is whispering, "Here, this is as far as you can go. Beyond this, I become something else." What lies beyond? What happens when you try to peer past the Planck length to measure distances shorter than the shortest distance, to capture moments briefer than the briefest moment? That's where things get strange, where the smooth certainties of Einstein's relativity meet the probabilistic shadows of quantum mechanics, where space-time, the four-dimensional stage on which reality performs, stops being smooth, stops being predictable, stops perhaps being real in any way we'd recognize. Some nights when you look up at the stars, you're looking at light that has traveled for billions of years across billions of miles. Smooth, steady, predictable. But if you could somehow zoom in down, past atoms, past particles, past the Planck length itself, that light and the space it travels through would look nothing like the calm night sky. It would look like chaos, like a storm in a teacup that never ends, like reality boiling. And the strangest part, we can't see it. We may never see it. The Planck scale is so far beyond our instruments, beyond our colliders and telescopes, that reaching it might require energies we'll never command, distances we'll never probe. And yet, we know it's there. Or at least we think we do. The mathematics points to it. The logic demands it. The universe seems to insist. So, we're left with a kind of cosmic humility, a recognition that there are edges to knowledge itself, Not because we lack imagination or technology, but because reality at its deepest might be stranger than we can think. Planck found the door, but he didn't walk through it. That would take others. Brave, curious minds willing to stand at the edge of the known and imagine what lies beyond. Why do we care about something so small, so distant from everyday life? Why spend time on a quiet night like this, thinking about lengths and times that have no bearing on our world? Because it's where the story starts. Every story of the universe begins at the Planck scale. The Big Bang itself, if there was one, happened in a flash no longer than the Planck time. In that first instant, the universe was smaller than the Planck length. Everything, all the space, all the matter, all the light, that would one day become galaxies and stars, and you existed in a point so small it defies description. To understand the beginning, we have to understand the Planck scale. To understand black holes, the densest objects in the cosmos, we have to understand what happens when matter compresses down to the Planck length. To understand gravity, the force that holds galaxies together and pulls apples to the ground, we have to understand how it behaves when it's no longer weak, when it becomes as strong as the other forces, when quantum mechanics can no longer ignore it. The Planck scale is the meeting place, the crossroads where all the big questions intersect, where gravity meets quantum, where time meets space, where something becomes nothing, or nothing becomes something. And it's beautiful in a way, that the universe has this hidden layer, this secret basement beneath the basement, a place we can't touch but can only describe with mathematics and metaphor. It reminds us that reality is not obvious, that the world is not just what we see and feel, that there are depths beneath depths, mysteries beneath mysteries. Planck gave us a key, a small golden key made of 3 numbers, and when we turn it, we hear a door creak open somewhere in the dark. We don't know what's inside, not fully, but we can hear it breathing. We can feel its presence. Some scientists believe the Planck scale is where all 4 forces of nature become one, where the electromagnetic force, the weak nuclear force, the strong nuclear force, and gravity, all distinct in our everyday world, merge into a single unified force, a super force, the force that governed the universe in its first breath. Others believe the Planck scale is where space-time itself is made, where quantum loops or strings or some other fundamental entity weaves the fabric of reality stitch by stitch, where space is not a container for things, but a thing itself, built from smaller things, like a tapestry from threads. Still others wonder if the Planck scale is a limit we impose, not a limit the universe respects. That perhaps beyond it there are other scales, other layers, other rules. That we're standing on a shore calling it the edge of the world, when really it's just the edge of what we can see. We don't know yet. And that's okay. The not knowing is part of the journey. So here we are in the quiet at the edge of the smallest. Planck's gift to us is not certainty. It's a question, a direction, a place to look. Tonight we'll follow that direction together. We'll drift through the physics of the very small, the very fast, the very strange. We'll meet the foam that bubbles beneath space-time, the strings that might sing reality into being the black holes that exist for less than a heartbeat. We'll travel to the beginning of time, when everything was Planck-sized, and forward to the laboratories where scientists dream of touching that scale. You don't need to hold on to every detail. Let them flow past like water. Let the ideas settle where they want. Rest in the strangeness. Let curiosity do the listening. Because the truth is, we're not here to solve anything. We're here to wonder, to feel the vastness and the tininess all at once. To be reminded that the universe is not a puzzle we've finished, but a mystery we're still learning how to ask questions about. Planck measured the immeasurable. He named the unnameable. He found the place where mathematics points and says, "Here, beyond this, something changes." And in doing so, he gave us permission to dream at the smallest scales, to imagine what reality becomes when you shrink it past recognition, to stand at the edge of knowledge and look into the dark with wonder instead of fear. So take a breath. Let your mind settle. Feel the weight of your body, the pull of gravity, the passage of time. All of these things so familiar, so constant, emerge from something deeper, something we're only beginning to touch. The Planck scale waits for no one. It's been there since the beginning. It will be there at the end. A quiet boundary, a threshold, a whisper in the dark that says, reality is stranger than you think. Now, as the night deepens and your breathing slows, we'll step a little closer to that strangeness. Not too fast, not too far. Just enough to glimpse the edges of a world that lives beneath the world we know. A place where units of measurement become doorways, where constants become clues, and where the smallest things hold the largest mysteries. 3 numbers, that's all it took. Max Planck sat with 3 constants of nature, the speed of light, the gravitational constant, and his quantum constant, and from them he built a ruler. Not a ruler you could hold, not a ruler made of wood or metal, a ruler made of pure mathematics, a ruler that measures the universe's absolute limits. And here's what makes it extraordinary. Any intelligent being anywhere in the cosmos would build the same ruler, the same units, the same boundaries. It's as if the universe left instructions hidden in plain sight. Let's understand how this invisible ruler works, how 3 simple numbers weave together to form the fabric of cosmic measurement. Because once you see it, you'll realize that the Planck units aren't human inventions. They're discoveries, truths written into existence itself. The speed of light represented by the letter c is 299,792,458 meters per second. Scientists have measured it with extraordinary precision. It's the cosmic speed limit. Nothing moves faster, not particles, not information, not even gravity's pull. Then there's the gravitational constant written as capital G. It describes how strongly mass attracts mass, how the Earth holds you to its surface, how the sun keeps planets in orbit, how galaxies spiral through space without flying apart. G is weaker than you might think. Gravity is the gentlest of all forces, but it reaches infinitely far. Finally, there's the reduced Planck constant written as h bar, or. This is Planck's own discovery, the quantum of action, the smallest chunk of angular momentum that can exist. It governs how electrons orbit atoms, how photons carry energy, how uncertainty weaves through every measurement. It's the heartbeat of quantum mechanics. 3 constants, 3 descriptions of reality. And when you combine them in just the right way, they reveal something hidden. Take the speed of light and square it. Take h bar and multiply it by c. Divide by g. Take the square root. What emerges is a length. The Planck length. 1.6 times 10 to the negative 35 meters. It sounds like magic, but it's just mathematics, the universe showing its hand. Scientists suggest this length is fundamental, not arbitrary like a meter or a mile, not based on the size of Earth or the swing of a pendulum. It emerges from the laws of physics themselves. It's woven into the fabric of space-time, quantum mechanics, and gravity. Any civilization, human alien or otherwise, would calculate exactly this value. Imagine meeting someone from another galaxy. You don't speak their language. You don't share their culture. But if they understand physics, they'll know the Planck length. It's a universal handshake, a cosmic greeting written in numbers. Now, let's talk about time. The Planck time is how long it takes light to travel 1 Planck length. It's approximately 5.4 times 10 to the negative 44 seconds. That's a decimal point, followed by 43 zeros, and then a 5. It's so brief that nothing we know can happen faster. In 1 Planck time, even light racing at its maximum speed barely moves a Planck length. Think of it as the universe's smallest tick of a clock, the shortest moment that has meaning. If time itself has pixels, the Planck time is the size of 1 pixel. Below that duration, some researchers believe the very concept of time dissolves. There's no before or after in any meaningful sense. Time becomes something else, something we don't yet have words for. And there's mass too, the Planck mass. This one surprises people. While the Planck length and time are unimaginably small, the Planck mass is not. It's about 2.2 times 10 to the negative 8 kilograms, roughly 22 micrograms, about the mass of a flea's egg or a grain of fine sand. That doesn't sound extreme, but here's the twist. If you compress that mass into a space the size of the Planck length, you'd create a black hole, the smallest possible black hole, a quantum black hole that would evaporate almost instantly through what we call Hawking radiation. The Planck mass tells us something profound. It's the point where quantum mechanics and gravity become equals, where neither force dominates, where the rules of the very small collide with the rules of the very large. At everyday energies, the energy of a rolling ball, a flying bird, a speeding car gravity is almost negligible. It's the weakest force by far. Electromagnetism is 10 to the 38th times stronger. But at the Planck scale, gravity roars to life. It becomes as powerful as the other forces. It bends space-time so intensely that quantum effects cannot be ignored. This is why physicists say the Planck scale is where quantum gravity lives, where Einstein's relativity meets Heisenberg's uncertainty, where the smooth meets the probabilistic, where certainty crumbles. Let's pause here and feel the scale again, but differently this time. Imagine you're holding a proton, tiny, right, the nucleus of a hydrogen atom. Now, imagine shrinking yourself down. You dive inside the proton, inside the quarks that make it up. You keep shrinking, smaller, smaller. Eventually, you reach the Planck length. At that moment, you've shrunk by a factor of about 10 to the 20th power compared to the proton. That's 100 billion times smaller. To put it another way, the ratio between a proton and the Planck length is roughly the same as the ratio between the entire observable universe and the distance from Tokyo to Chicago. One is cosmically vast. The other is a 14-hour flight. Yet, proportionally, they're the same comparison. This is the Planck length, a place so small that our metaphors start to fail. Now here's where it gets strange and beautiful. The Planck units aren't just theoretical curiosities. They mark real boundaries. Scientists believe that attempting to measure anything smaller than the Planck length would require so much energy that you'd create a black hole. The very act of measurement would destroy the thing you're trying to measure. It's as if the universe has a privacy setting, a do not disturb sign at the smallest scales. Push too hard and reality pushes back. This has profound implications. It means there might be no such thing as infinite divisibility. You can't keep cutting space in half forever. You can't zoom in endlessly. At some point at the Planck length, the zoom ends. Space becomes discrete, grainy, pixelated in a sense. Some theories suggest that space-time itself is made of Planck-length chunks, tiny units that can't be divided further. Like how a digital photograph is made of pixels, reality might be made of Planck-scale units, smooth from a distance but granular up close. This would change everything. It would mean that space and time aren't continuous fabrics, but discrete structures. It would mean that the universe is in some sense digital, built from fundamental bits of existence. But here's the problem. We can't test this. Not yet. Maybe not ever. The energy required to probe the Planck scale is called the Planck energy. It's approximately 1.2 times 10 to the 19 giga-electron volts. That's enormous. The Large Hadron Collider, the most powerful particle accelerator humanity has ever built, reaches energies of about 10 tera-electron volts. The Planck energy is a quadrillion times higher. To build a collider that could reach Planck-scale energies, you'd need a machine the size of the Milky Way galaxy, powered by more energy than exists in all the stars we can see. It's not a question of technology. It's a question of fundamental limits, so we're left with theory, with mathematics, with imagination, We can calculate what happens at the Planck scale, but we can't observe it directly. We're like astronomers trying to study the surface of a distant star, except this star is so far away that its light will never reach us. And yet, the Planck units guide us. They tell us where to look, what questions to ask. They're signposts pointing toward the deepest truths of reality. Consider temperature. There's a Planck temperature too. It's about 10 to the 32 Kelvin, the hottest possible temperature. At this heat, particles move so fast, collide so violently, that the very structure of space-time begins to melt. Scientists believe the universe reached this temperature in the first moments after the Big Bang. For an instant shorter than the Planck time, everything was this hot. There's also a Planck charge, a Planck voltage, even a Planck impedance. Every physical quantity has a natural unit formed from Cg, and it's as if nature wrote a complete dictionary of measurement, and we're only now learning to read it. Why does this matter? Why spend a quiet evening thinking about units and constants? Because they reveal something about the universe's architecture, about its design. The Planck units aren't arbitrary. They emerge from the interplay of light gravity and quantum mechanics, from the three pillars that hold up reality as we know it. And they suggest that the universe has edges. Not edges in space, but edges in concept, limits beyond which our current understanding cannot go. The Planck scale isn't a wall we hit because we're not smart enough. It's a boundary written into the laws of physics themselves. Some scientists believe this boundary is where all the forces unify, where electromagnetism, the weak force, the strong force, and gravity distinct in our world merge into one, a superforce, the force that governed the universe's first breath. Others believe the Planck scale is where space-time is woven, where quantum loops or strings or some other fundamental entity stitches reality together, where the fabric isn't given but made. Still others suspect the Planck scale is an illusion, a limit of our current theories, not a limit of nature, that beyond it there are deeper layers, smaller scales, stranger physics. We don't know, not yet. But the beauty is in the seeking. Planck gave us a language, a way to talk about the extremes, a system of units that doesn't depend on human choices or historical accidents. It depends only on the universe itself, on constants that were here before us and will remain after we're gone. When we measure in Planck units, we're speaking the universe's native language. We're translating the cosmos into its own terms. And in doing so, we glimpse something extraordinary, that nature has preferences, structure, boundaries. That reality isn't an infinite featureless expanse, but a place with edges, corners, limits. The Planck length is the smallest meaningful distance. The Planck time is the briefest meaningful moment. The Planck mass is the point where gravity wakes up. These aren't approximations. They're not rough guesses. They're exact, determined by the constants of nature themselves. And they're waiting. Waiting for us to understand what they mean. Waiting for theories that can describe what happens at those scales. Waiting for a physics that can unite quantum mechanics and gravity without contradiction. Planck didn't know what he'd built. He was solving a problem about glowing metal. But in the process, he handed us a key, a ruler made of light gravity and quantum action, a tool for measuring the immeasurable. So the next time you look at a ruler, think about this invisible one, the one that exists in equations and constants, the one that any mind anywhere in the universe would recognize, the one that measures not what we've made, but what the cosmos has always been. It's humbling in a way, to realize that the universe came with its own system of measurement, that we're not inventing physics, we're discovering it, translating it, learning to speak a language that existed before words. And as we drift deeper into this strange territory as the night settles and your thoughts slow, remember every measurement you've ever made, every meter, every second, every kilogram, is just an approximation, a human convenience. But the Planck units are different. They're fundamental, true, written into the code of existence itself. The invisible ruler measures the immeasurable, and it points always towards something deeper, something we're only beginning to understand. A place where space-time and matter stop being separate things and become something else, something strange, something waiting in the smallest corners of reality, where the rules we know start to whisper their secrets. Picture a perfectly still pond. The surface is smooth as glass. You can see your reflection, the sky, the trees. Everything is clear, predictable. Einstein spent his life describing that pond, the smooth, continuous fabric of space-time. He showed us how it bends, how it curves, how massive objects create wells in its surface. But when you get close enough, impossibly close, the pond stops being smooth. It ripples, it churns, it becomes something wild. And at the Planck scale, Einstein's beautiful pond shatters completely. The smooth geometry of space-time, the foundation of everything we know about gravity and the universe, breaks down. And what replaces it is far stranger than anyone imagined. In 1915, Albert Einstein published his masterpiece, The Theory of General Relativity. It was a revolution, a complete reimagining of gravity. Newton had described gravity as a force, an invisible pull between masses. But Einstein said no, gravity isn't a force, it's geometry. M-mass bends space-time, and objects moving through the bent space-time follow curved paths. The Earth doesn't orbit the Sun because of some mysterious attraction. It orbits because the Sun warps the fabric of space and time around it, and the Earth simply follows the straightest possible path through that warped geometry. It's elegant, beautiful, and for over a century, it's held up to every test we've thrown at it. We've measured the bending of starlight around the Sun. We've detected gravitational waves, ripples in space-time itself, from colliding black holes billions of light years away. We've watched time slow down near massive objects, exactly as Einstein predicted. General relativity describes space-time as a smooth, continuous manifold, a four-dimensional fabric where every point connects seamlessly to every other point, where you can zoom in infinitely and still find smoothness, where geometry is well-defined, predictable, classical. But there's a problem. A crack in the foundation. Einstein's space-time is smooth. Quantum mechanics is not. And at the Planck scale, the quantum wins. Let's talk about Werner Heisenberg. In 1927, he discovered something that would haunt physics forever, the uncertainty principle. It states that you cannot know both the position and momentum of a particle with perfect precision. The more accurately you measure one, the less accurately you know the other. This isn't a flaw in our instruments. It's not a limitation of technology. It's fundamental, built into the fabric of quantum reality. Particles don't have exact positions and exact momenta simultaneously. Those properties are inherently fuzzy, probabilistic, uncertain. For most everyday purposes, this uncertainty is negligible. Atoms, molecules, even tiny grains of dust, they're large enough that quantum uncertainty doesn't matter much. But as you probe smaller scales, the uncertainty grows. It dominates. It becomes impossible to ignore. And here's where Einstein's dream breaks. At the Planck length, the uncertainty principle collides with the curvature of space-time. To measure a distance as small as the Planck length, you'd need to confine a particle, say, a photon, to a region that small. But Heisenberg's uncertainty tells us that confining a particle to such a tiny space requires enormous momentum, enormous energy. How much energy enough to create a black hole? Scientists have calculated this carefully. If you try to probe distances smaller than the Planck length by using increasingly energetic particles, you eventually reach a point where the energy density is so high that space-time itself collapses. A black hole forms. The very act of measurement creates a singularity that swallows the information you were trying to obtain. It's as if the universe says you can look, but not too closely. Push too hard, and I'll hide the answer behind an event horizon. This is why physicists say that the Planck length is the smallest meaningful distance. Not because smaller distances don't exist in some abstract sense, but because we can't measure them, can't probe them, can't even define what distance means at those scales without running into contradictions. But it gets stranger. Quantum mechanics tells us that energy and time are also subject to uncertainty. The more precisely you know when an event occurs, the less precisely you know its energy, and vice versa. This means that even in empty space, what we call the vacuum energy is constantly fluctuating, popping in and out of existence, borrowing energy from the universe for brief moments, then paying it back. These fluctuations are tiny at large scales, but at the Planck scale, they become violent. Space-time itself starts to fluctuate. The smooth fabric Einstein described begins to ripple, to shake, to lose its definition. Imagine trying to draw a straight line on a piece of paper, but the paper is trembling, vibrating, folding in on itself. At some point, the line stops making sense. You can't define straight anymore. The geometry becomes chaotic. That's what happens to space-time at the Planck scale. The quantum fluctuations are so large that the very concept of a smooth geometry breaks down. Distances become uncertain. Durations become uncertain. Even the dimensionality of space, the fact that we live in 3 spatial dimensions, becomes blurry. Some researchers suggest that at the Planck scale, space-time might have more dimensions, or fewer, or dimensions that change from point to point. The smooth, predictable stage on which events unfold becomes a churning sea of possibilities. This is not speculation. It's a consequence of combining Einstein's gravity with Heisenberg's uncertainty. 2 of the most successful theories in physics pointing toward the same conclusion: at the Planck scale, space-time stops being smooth. Let's think about what this means. In our everyday world, we take space and time for granted. Space is where things happen. Time is when things happen. They're the stage, the background, the container for events. They're absolute, fixed, real. But Einstein already challenged that. He showed us that space and time are relative, that they bend, that they're woven together into a single fabric called space-time, that moving fast or standing near a massive object changes how you experience time. That simultaneity is an illusion. What's now for you might be then for someone else. And yet, even in Einstein's relativity, space-time is real. It's a thing. It has geometry, it has structure, it follows equations, it's smooth. But at the Planck scale, even that dissolves. Space-time stops being a fixed stage and becomes a dynamic, fluctuating, probabilistic something. A something we don't fully understand. A something that might not even be fundamental, but emergent, built from deeper ingredients we haven't identified yet. Think about water. From a distance, water looks smooth, continuous. You can describe it with equations for fluid flow. But zoom in and you see molecules, discrete particles bouncing around. The smoothness is an illusion created by averaging over many molecules. Maybe space-time is like that. Smooth at large scales, but discrete and chaotic at the Planck scale, made of something smaller, something that doesn't look like space or time at all. This idea terrified some physicists and excited others. In the 1950s, several physicists began to realize that quantum field theory, the framework we use to describe particles and forces, fails when applied to gravity. The equations produce infinities, nonsensical results. And these infinities get worse, not better, as you probe smaller distances. For the other forces, electromagnetism, the weak and strong nuclear forces, physicists developed a technique called renormalization, a way to tame the infinities, to absorb them into redefined constants and extract meaningful predictions. It works brilliantly. But gravity is different. Gravity is non-renormalizable. The infinities multiply, they spread, they infect every calculation. No amount of mathematical trickery can make them go away. This suggested something profound. Our current theories of gravity and quantum mechanics are incomplete. They work in their respective domains: general relativity for large scales, quantum mechanics for small scales, but they cannot both be true at the Planck scale. Something has to give. Lev Landau, a brilliant Soviet physicist, argued in the 1950s that the Planck scale marked the end of quantum field theory, that beyond it, new physics would emerge, physics we couldn't even imagine yet. Oscar Klein suggested that space-time might have extra dimensions curled up so small we can't see them, that at the Planck scale, these dimensions might unfurl, revealing a richer structure. Others wondered if space-time itself was an approximation, a low-energy description of something more fundamental, like how thermodynamics emerges from statistical mechanics, or how chemistry emerges from quantum physics. Maybe space-time emerges from something deeper. But what could be deeper than space and time? What could be more fundamental than the stage on which everything else plays out? That question still haunts physics. And the Planck scale is where it becomes unavoidable. Here's another way to think about it. Imagine you're watching a movie. On the screen, characters move smoothly. Time flows naturally. Space is continuous. But if you examine the film itself, you find discrete frames. 24 images per second, each slightly different. The smoothness is an illusion created by showing the frames quickly. Maybe the universe is like that. Smooth because we're watching it at low resolution. But at the Planck scale, at the level of individual frames, it's discrete, choppy, fundamentally different from what we perceive. This would explain why our smooth, continuous theories break down at the Planck scale. We're trying to use calculus, a tool for continuous functions, to describe something fundamentally discrete. It's like trying to describe a staircase with a smooth ramp. It works as an approximation, but up close the steps are undeniable. Some theories take this idea seriously. Loop quantum gravity, for instance, suggests that space is made of tiny loops, quantum excitations of geometry itself. These loops are about a Planck length in size. They connect to form networks, and these networks are what we perceive as smooth space-time. In this view, space isn't continuous. It's woven, stitched together from discrete units. And at the Planck scale, you can see the stitching. Other theories suggest that space-time is holographic, that the three-dimensional space we experience is actually encoded on a two-dimensional surface like a hologram, that the Planck scale is where this encoding becomes apparent. Still others propose that space-time emerges from quantum entanglement, that the connections between particles' spooky action at a distance, as Einstein called it, are what create the illusion of space, that if you could somehow untangle everything, space would vanish. These are radical ideas, strange ideas, but they're taken seriously because the alternative is worse, accepting that we simply don't know what happens at the Planck scale, that our theories are silent, that the universe keeps secrets we may never crack. And here's the humbling part. We might be wrong about all of it. The Planck scale might not be special at all. It might just be where our current theories fail, not where nature changes. There could be layers beneath layers, scales beneath scales, physics beneath physics. The Planck length might be like the sound barrier, once thought to be an impenetrable wall, but really just a transition to a new regime. We don't know. We can't see. We're fumbling in the dark, guided only by mathematics and intuition. But that's okay. That's the beauty of it. The Planck scale is a frontier, a place where knowledge ends and wonder begins, where Einstein's smooth space-time meets Heisenberg's quantum uncertainty, and neither emerges victorious, where the rules we've spent centuries discovering start to whisper, "There's more. Keep looking." So, what do we lose when space-time stops being smooth? We lose certainty. We lose the comfort of a fixed stage. We lose the ability to say with confidence, "This event happened here at this time," because here and this time stop having sharp meanings. But we gain something too. We gain a glimpse of something deeper, a hint that reality is not what it seems, that the universe is not a machine ticking along predictably, but a living, breathing, fluctuating mystery, that beneath the smoothness there's texture, complexity, strangeness. Einstein gave us curved space-time. Heisenberg gave us quantum uncertainty. And at the Planck scale, they shake hands and point towards something neither could have imagined alone. Something that makes the universe far richer than we thought, far stranger, far more alive. As the night deepens and your breath slows, imagine that smooth pond again. But now, imagine diving beneath its surface. The deeper you go, the colder it gets, the darker. And at some point, you reach a depth where the water stops being water, where it becomes something else, something ancient, something that predates the pond itself. That's the Planck scale, a depth where the familiar dissolves and the universe reveals its hidden architecture, one quantum ripple at a time. Empty space isn't empty. That's the first thing to understand. What looks like nothing, the vacuum between stars, the gap between atoms, the silence between heartbeats, is actually seething, bubbling, alive with activity we cannot see. And at the Planck scale, that activity becomes so violent, so chaotic, that space itself stops being space. It becomes foam, quantum foam, a churning sea of possibilities where geometry itself is born and dies in fractions of a fraction of a second. John Wheeler saw this first, and what he imagined changed everything. The year was 1955. John Archibald Wheeler, a physicist at Princeton, a man who had worked on the atomic bomb and mentored Richard Feynman, was thinking about quantum mechanics and gravity, about what happens when you combine Heisenberg's uncertainty with Einstein's curved space-time. And he realized something extraordinary. If energy and time are uncertain, and if energy curves space-time, then space-time itself must be uncertain. It must fluctuate. And at small enough scales at the Planck scale, those fluctuations would become enormous, wild, uncontrollable. Wheeler called it quantum foam, sometimes space-time foam. The idea that at the smallest scales, the smooth fabric of space-time Einstein had described would dissolve into a frothing, bubbling sea, a place where geometry itself is constantly being created and destroyed, where tiny wormholes open and close, where the number of dimensions flickers, where the very topology of space changes from moment to moment. It was a radical vision, and for decades it remained just that, a vision, a metaphor, a way of imagining what might happen in a regime no experiment could reach. But Wheeler was right to imagine it, because when you take quantum mechanics seriously when you apply it to space-time itself, the foam is unavoidable. Let's understand why. In quantum mechanics, the vacuum is not empty. It's filled with what physicists call virtual particles. These are not particles in the usual sense. They're quantum fluctuations, temporary violations of energy conservation allowed by Heisenberg's uncertainty principle. A particle and its antiparticle can spontaneously appear out of nothing, exist for a brief moment, and then annihilate back into nothing. An electron and a positron, a quark and an antiquark. Even a photon, which is its own antiparticle, can flicker in and out of existence. How long do they last? It depends on their energy. Higher energy fluctuations must disappear faster. The relationship is exact, determined by Heisenberg's equation. For a fluctuation with energy, E, the maximum lifetime is roughly h bar divided by E. At everyday energies, these fluctuations are tiny, negligible. But as you probe smaller distances, which requires higher energies, the fluctuations grow. They become more frequent, more energetic, more real in a sense. And at the Planck scale, they become catastrophic. Scientists calculate that at Planck scale energies, the vacuum is filled with virtual particles appearing and disappearing at an incredible rate. Not just particles, but entire geometries. Tiny black holes forming and evaporating. Wormholes connecting distant points in space, then collapsing. Bubbles of space-time where the usual number of dimensions doesn't apply. Wheeler imagined this as foam, like the foam on ocean waves where bubbles form and pop constantly. Except this foam is made of space-time itself. Each bubble is a quantum fluctuation of geometry. Each pop is a return to the average structure. From a distance from our everyday perspective, the foam averages out. We see smooth space, predictable time, but up close at the Planck length, the foam is undeniable. Space-time becomes a chaotic, ever-changing landscape. It's beautiful in a way. The idea that the stage on which reality performs is not fixed but dynamic, that even the vacuum, the closest thing we have to nothing, is actually teeming with activity. That stillness is an illusion created by distance. But it's also deeply strange, because if space-time is foaming at the Planck scale, then many of our basic concepts stop working. What does it mean to say two events are next to each other if the space between them is constantly fluctuating? What does it mean to say one event happens before another if time itself is uncertain? What does distance even mean in a foam? These aren't philosophical questions. They're physical ones, and they don't have clear answers yet. Wheeler proposed the foam in the 1950s, but it took decades for physicists to develop the mathematical tools to describe it rigorously, to move beyond metaphor and into equations. One of the key insights came from understanding vacuum energy, the energy of empty space. In quantum field theory, even the vacuum has energy because of those constant fluctuations. Virtual particles popping in and out, fields oscillating at every point. When you try to calculate the total vacuum energy, you get an absurd result: infinite. Because there are fluctuations at every energy scale, and when you add them all up, the sum diverges. Physicists found a way around this. They introduced a cutoff. They said, we'll only count fluctuations up to a certain energy. Beyond that, we assume something else happens. Some new physics takes over, and the natural cutoff is the Planck energy, because beyond that, quantum gravity effects become important. The vacuum fluctuations would be so energetic that they'd create black holes. Space-time itself would break down. But even with this cutoff, the vacuum energy is enormous. Scientists estimate it at about 10 to the 93rd grams per cubic centimeter. That's a density far, far higher than anything we observe in the universe. This creates a puzzle, a profound puzzle. Because we know the vacuum has energy, we can measure it through the cosmological constant, the thing that's causing the universe to expand faster and faster. But the measured value is about 10 to the 120 times smaller than the theoretical prediction. Why, no one knows. It's called the cosmological constant problem, and it's one of the deepest mysteries in physics. But it's intimately connected to Wheeler's foam, to the idea that space-time is fluctuating violently at the Planck scale. Some researchers suggest that the foam itself might cancel out its own energy, that the positive and negative fluctuations balance in some subtle way we don't yet understand, that the universe is cleverer than we thought. Others propose that the foam's energy is real, but it doesn't affect large-scale space-time because the fluctuations are so small and so fast that they average to nearly zero. Like how the rapid vibrations of atoms in a solid don't affect its overall shape. Still others wonder if the foam is trying to tell us something, that space-time is not fundamental, that it emerges from something deeper, something that doesn't have these energy problems. But let's return to Wheeler's vision, to the foam itself. Imagine zooming in on a piece of space-time. At first it looks smooth, flat, Euclidean, the kind of space you learned about in school. But as you zoom in further, you start to see wrinkles, tiny bumps and dips. The geometry is no longer perfectly flat. Zoom in more, and the wrinkles become larger, more chaotic. The space starts to look rough, textured, like a magnified photograph where the pixels become visible. At the Planck scale, the texture dominates. The space is no longer anything like a smooth manifold. It's a seething mass of fluctuations, tiny regions where space curves one way then another, where time speeds up and slows down, where wormhole shortcuts through space-time appear and vanish in less than a Planck time. Wheeler suggested that these wormholes might connect distant points in space. that the foam might have a multiply-connected topology. That space-time at the smallest scales might be full of handles, bridges, tunnels, a place far richer than the simple smooth geometry we see. In fact, some calculations suggest that the foam might have 1 unit of topological complexity per Planck volume, 1 wormhole handle on average in every cube of space, 1 Planck length on a side. That's an almost incomprehensible density of structure. If this is true, then space-time is not a simple 4-dimensional fabric. It's an incredibly complex high-dimensional structure that only looks 4-dimensional when you step back and average over many Planck volumes. It's like a piece of cloth. From a distance it looks smooth, but under a microscope you see fibers woven together. And under an even more powerful microscope, you see that each fiber is made of molecules, and each molecule is made of atoms. The apparent simplicity is an illusion created by coarse graining. Wheeler's foam suggests that space-time is similar, simple and smooth at large scales, unbelievably complex at small scales. But here's the challenge: we can't see it, not directly. The Planck scale is far, far beyond the reach of any experiment we can currently perform. So, how do we test this idea? How do we know if Wheeler's foam is real or just a beautiful mathematical fiction? Scientists have tried. Oh, how they've tried. One prediction is that the foam should affect light traveling through it. Photons should scatter slightly as they pass through the turbulent geometry. This scattering should blur distant images like fog blurs a distant mountain. Astronomers have looked. They've used the Chandra X-ray Observatory to study quasars' incredibly distant, incredibly bright objects. They've used the Fermi Gamma Ray Space Telescope to watch high-energy photons from cosmic sources. They've measured the light from gamma-ray bursts with ground-based observatories like Veritas, and they've found nothing. No blurring. No scattering. The images are sharp as they should be if space-time were perfectly smooth. This was disappointing, but also revealing. It tells us that if the foam exists, it must be smaller than expected. The fluctuations must be confined to scales even tinier than the Planck length. Or perhaps they're arranged in such a way that they don't scatter light. Or perhaps the foam is there, but its effects are too subtle to detect with current technology. Some experiments in 2005 seem to show a variation in the speed of light for photons of different energies arriving from a blazar called Markarian 501. This could have been evidence for space-time graininess for the foam, but follow-up experiments found no such effect. The result couldn't be replicated, so the foam remains elusive, predicted by theory, required by the mathematics, but invisible to our instruments. And yet, physicists continue to believe in it, or at least to take it seriously, because it's what happens when you combine quantum mechanics and general relativity, when you let space-time obey the uncertainty principle, when you follow the equations to their logical conclusion. Wheeler was not deterred by the lack of evidence. He believed in the foam because the logic demanded it, because it was beautiful, because it suggested that the universe was more alive, more dynamic, more interesting than anyone had imagined. He once said, "Time is nature's way of keeping everything from happening at once." And then later in life, he might have added, "And the quantum foam is nature's way of making sure that at the smallest scales, everything does happen at once." In Wheeler's foam, past and future blur. Cause and effect become ambiguous. The distinction between here and there softens. It's a place where the classical concepts we rely on, the ones that make sense in our macroscopic world, simply don't apply. And perhaps that's the point. Perhaps the foam is nature's way of telling us that space-time is not fundamental, that it's emergent, that it arises from something more basic, something that doesn't look like space or time at all. Some modern theories embrace this. Loop quantum gravity, for instance, describes space as a network of quantum loops. Each loop is about a Planck length around. The loops connect and form a web, and this web is what we perceive as space-time. The foam in this picture is the constant rearrangement of loops, the network fluctuating, reconfiguring, dancing at the quantum level. String theory offers a different picture. Strings vibrating in extra dimensions create the illusion of space-time. The foam might be fluctuations in those extra dimensions. Or it might be the strings themselves moving and interacting in ways that produce temporary, unstable geometries. Causal set theory goes even further. It suggests that space-time is not continuous at all, but discrete, made of point-like events connected by causal relationships. The foam would be the quantum uncertainty in those relationships, the fuzziness in which events are truly connected. Each theory has its own version of the foam, its own way of making Wheeler's vision mathematically precise. But all of them agree on one thing: at the Planck scale, space-time is not what it seems. And maybe that's enough. Maybe the foam doesn't need to be directly observed to be real. Maybe its reality is in the mathematics, in the way it emerges inevitably from the marriage of quantum mechanics and gravity, in the way it forces us to rethink what we mean by space and time. Wheeler understood this. He understood that physics is not just about measuring things. It's about imagining them, about following the logic of our theories into strange new territories and seeing what we find. The foam is strange, no question. It's a place where geometry is born and dies, where nothing is stable, where the stage itself is performing. But it's also perhaps the truest picture we have of what space-time is at its deepest level. Not a stage, not a container, not a background, but a participant, a player in its own right. Something dynamic, alive, and far more mysterious than the smooth, predictable fabric we thought we knew. So, as the night settles deeper and your thoughts begin to soften, picture this: beneath every moment, beneath every inch of space, there's a storm. A quantum storm that never stops. Bubbles forming and popping, wormholes opening and closing, dimensions flickering in and out of existence. It's invisible, silent, but it's there, always holding everything together by constantly falling apart. Wheeler's foam, the hidden texture of reality, the dream that space-time dreams when no one's watching. 4 forces hold the universe together. 4 fundamental interactions that govern everything from the collision of galaxies to the beating of your heart. Electromagnetism, the weak nuclear force, the strong nuclear force, and gravity. 3 of them speak the same language, the language of quantum mechanics. They've been unified, understood, woven into a single mathematical framework. But gravity stands apart, silent, separate, refusing to join. And at the Planck scale, this refusal becomes a crisis, because that's where gravity finally wakes up, where it stops being the weakest force and becomes an equal, where the quiet giant demands to be heard. Why won't gravity play by the quantum rules, and what happens when it finally does? In our everyday world, gravity is weak, astonishingly weak. You can feel this yourself. Pick up a paperclip with a small magnet. That tiny magnet, a few grams of metal, overcomes the gravitational pull of the entire Earth. 6 billion trillion kilograms of mass pulling down on that paperclip, and a child's toy defeats it effortlessly. This is not an accident. Gravity is intrinsically weaker than the other forces. Scientists have measured this precisely. The electromagnetic force between 2 electrons is about 10 to the 42nd power, stronger than the gravitational force between them. That's a 1 followed by 42 zeros. It's not even close. The weak nuclear force, the one responsible for radioactive decay for the sun's fusion, is also far stronger than gravity at small scales. The strong nuclear force, the one that holds atomic nuclei together against electromagnetic repulsion, is stronger still. Gravity is the gentle giant. It only matters when you have enormous amounts of mass: planets, stars, galaxies. For individual particles, for quantum systems, for anything happening at small scales, gravity is essentially negligible. And so, for most of the 20th century, physicists ignored it. They built quantum mechanics without gravity. They unified electromagnetism with the weak force into the electro-weak force. They described the strong force with quantum chromodynamics. They assembled everything into the Standard Model, a stunningly successful theory that describes all known particles and 3 of the 4 forces with breathtaking accuracy. But gravity wasn't included. It couldn't be included. Because gravity is described by Einstein's general relativity, a classical theory, a theory of smooth space-time and continuous curvature. And every attempt to make it quantum failed. This is the unification problem, the deepest puzzle in fundamental physics. How do you reconcile quantum mechanics? Discrete, probabilistic, uncertain, with general relativity, smooth, deterministic, geometric. At low energies, this doesn't matter. Gravity and quantum mechanics operate in separate domains. Gravity governs the motion of planets and the expansion of the universe. Quantum mechanics governs atoms and subatomic particles. They don't interfere with each other, but at the Planck scale, they collide, and neither one survives intact. Let's understand why gravity is different, why it resists quantization. In quantum field theory, forces are carried by particles. Electromagnetism is carried by photons. The weak force is carried by W and Z bosons. The strong force is carried by gluons. These are gauge bosons, quantum particles that mediate interactions between matter particles. And there's a number associated with each force, the coupling constant. It describes how strongly the force interacts. For electromagnetism, this is the fine structure constant, approximately 1 over 137. It's dimensionless, just a pure number. And it's constant, or nearly so, at the energies we typically probe. Actually, it's not quite constant. It changes slightly with energy. At higher energies, quantum effects cause the coupling to grow, but it grows slowly logarithmically. Even at the highest energies we can reach at particle colliders, like the Large Hadron Collider, the fine structure constant only increases from about 1 over 137 to about 1 over 128. The weak and strong forces have their own coupling constants, and they also change with energy, also logarithmically. This changing is called running in physics jargon. The couplings run with energy. Now, here's something beautiful. In certain extensions of the Standard Model, theories with extra symmetries, extra particles, the 3 coupling constants run in such a way that they meet at a single energy. They unify. All 3 forces become equally strong at around 10 to the 16th giga-electron volts. This is called grand unification, and it's tantalizing. It suggests that at very high energies, energies that existed in the early universe shortly after the Big Bang, the electromagnetic weak and strong forces were not separate. They were one, a single unified force. Only as the universe cooled did they split apart, taking on different strengths and different characters. Grand unification is not proven, but it's compelling. It explains certain patterns in the Standard Model. It predicts new particles and new interactions. And most importantly, it works mathematically. The 3 forces can be embedded into a larger symmetry group, a more encompassing framework. But gravity doesn't fit. Gravity is the outlier. For gravity, the coupling constant is not dimensionless. It's proportional to energy. The gravitational coupling at energy E is roughly E times the square root of Newton's gravitational constant G. This means it grows linearly with energy, not logarithmically. At low energies, the energies of everyday life, this coupling is tiny, around 10 to the negative 40. Gravity is unbelievably weak, but as you increase the energy, the coupling grows, and grows, and grows. At the Planck energy around 10 to the 19 giga-electron volts, the gravitational coupling reaches 1. Gravity becomes as strong as the other forces. It's no longer negligible. It's no longer the gentle giant. It's an equal player. And this is where everything breaks down. In quantum field theory, when a coupling constant reaches 1, the theory becomes strongly coupled. Perturbation theory. The main tool physicists use to calculate things stops working. You can no longer treat interactions as small corrections to free particle behavior. The interactions dominate. The mathematics becomes intractable. For the other forces, this isn't usually a problem. Their couplings can become strong, yes, but the theory itself remains well defined. The equations make sense. You just need different techniques to solve them. But for gravity, it's catastrophic. Because gravity is non-renormalizable. Let's unpack that word. Renormalization. In quantum field theory, when you calculate the probability of a process, say an electron emitting and reabsorbing a photon, you have to account for all possible intermediate states, all possible virtual particles that could appear and disappear during the process. And when you do this, you get infinities. The integrals diverge. The answer is infinite. This terrified physicists in the 1940s. It seemed like quantum field theory was fundamentally broken. How can a theory predict infinite probabilities? But then a solution was found. Renormalization. The idea is that the infinities can be absorbed into redefinitions of the fundamental parameters of the theory, the masses and charges of particles. You measure those parameters at some reference energy and then use those measured values in your calculations. The infinities disappear, or rather they hide inside the definitions of mass and charge. It's a bit like sweeping dust under a rug. The dust is still there, but you don't see it. And remarkably, it works. Quantum electrodynamics. The quantum theory of electromagnetism makes predictions accurate to 12 decimal places using renormalization. The weak and strong forces are also renormalizable. Their infinities can be tamed. The theories make sense. But gravity is different. When you try to quantize general relativity using the same techniques, you get infinities that cannot be absorbed. They multiply. They spread. Every order of perturbation theory introduces new types of infinities that require new parameters to absorb them. You'd need infinitely many parameters to define the theory. And a theory with infinitely many free parameters isn't a theory at all. It has no predictive power. It can't tell you anything. This is what physicists mean when they say gravity is non-renormalizable. It's not just that the calculations are hard. It's that the theory as formulated doesn't make sense at high energies. And the energy scale where it breaks down is the Planck energy, the place where gravity becomes strong, where quantum effects and gravitational effects are both important and cannot be separated. This was recognized in the 1930s by Lev Landau and others. Landau argued that quantum field theory must have a limit of validity, that there must be some energy scale beyond which it breaks down. And he suggested that scale was set by dimensional analysis by combining the fundamental constants of nature. In other words, the Planck scale. Oscar Klein around the same time suggested that gravity's problems might be solved by introducing extra dimensions. That perhaps space has more than 3 dimensions, but the extra ones are curled up invisible at everyday scales. At the Planck scale, these dimensions might unfurl, revealing a richer structure. This idea, extra dimensions, would later become central to string theory, but in the 1950s, it was just speculation. The problem remained. Gravity refuses to be quantized in the straightforward way. And without a quantum theory of gravity, we cannot describe what happens at the Planck scale. We cannot talk about the first moment after the Big Bang. We cannot describe the interiors of black holes. We cannot unify physics. But there's something deeper here, something that the non-renormalizability is trying to tell us. Maybe gravity is not a force like the others. Maybe it's not something that should be quantized in the same way. Maybe space-time itself, the thing gravity describes, is not fundamental. Think about it. Electromagnetism, the weak force, the strong force, they all operate within space-time. They describe interactions between particles that exist at definite locations in space and time. But gravity is space-time. It's the curvature of the stage itself. So, what does it mean to quantize the stage, to make the background probabilistic and uncertain? It's a conceptually different problem than quantizing a force. Some physicists believe this is the key insight, that quantum gravity is not about quantizing general relativity. It's about finding a more fundamental theory from which both quantum mechanics and general relativity emerge as approximations. This is a radical idea. It suggests that both of our most successful theories, quantum mechanics and general relativity, are effective theories. They work in their respective domains, but they're not the full story. There's a deeper theory beneath them, a theory that doesn't start with space-time or quantum fields, but with something more basic. And whatever that something is, it must operate at the Planck scale, because that's where both theories fail, where both theories point toward their own incompleteness. Now, here's another curious fact. At the Planck scale, all four forces might unify, not just the three we've already discussed, but all four, including gravity. Some researchers have calculated that if you extend the standard model in certain ways, by adding supersymmetry, for instance, the running coupling constants don't just meet at 10 to the 16th GeV. They continue running and meet gravity at the Planck scale. This would be extraordinary. It would mean that in the earliest moments of the universe, when energies were at the Planck scale, there was only one force, one unified interaction governing everything, a superforce. As the universe expanded and cooled, this superforce broke apart. First, gravity separated, becoming its own thing. Then the strong force split off. Then the electro-weak force divided into electromagnetism and the weak force. Four forces from one. This is deeply appealing. It suggests an elegant symmetry in nature, a fundamental simplicity beneath the apparent complexity. But it's speculative. We have no direct evidence for it. And without a working theory of quantum gravity, we can't even write down the equations for this unified force. Still, the idea persists, because the mathematics hints at it, because the Planck scale seems too important to be a coincidence, because physicists believe, perhaps irrationally, perhaps correctly, that nature is unified, that the four forces are not truly separate, but different faces of a single underlying reality. And gravity holds the key. Gravity is the holdout, the force that has to be brought into the fold before unification is complete. But gravity is stubborn. For a century, it's resisted every attempt to quantize it, to understand it in quantum terms, to make it speak the language of the other forces. Why? Is it because we're using the wrong approach, because we're asking the wrong questions? Or is it because gravity is fundamentally different, not a force at all, but an emergent phenomenon, a consequence of something deeper? We don't know yet. But the Planck scale is where the answer lives, where gravity stops being negligible and demands attention, where the gentle giant wakes up and reveals its true nature. And perhaps in that revealing, we'll find not just a theory of quantum gravity, but a theory of everything, a single framework that describes all forces, all particles, all of reality from the Planck scale to the cosmic scale. It's a beautiful dream. A dream that's driven physics for decades, and the dream always returns to the same place, the Planck scale, the crossroads where all paths meet, where quantum meets classical, where small meets large, where the four forces separate for so long might finally remember they were once one. So, as you rest here in the quiet, think about this. Every force you've ever experienced, the ground pushing up on your feet, the light entering your eyes, the fusion in the sun's core, the radioactive decay that warms Earth's interior, all of them might be echoes of a single ancient force, a force that existed for only the briefest moment in the first flash after creation and then splintered into the four we know. And somewhere deep in the mathematics, in the physics of the Planck scale, those four are still calling to each other, still remembering their unity, still waiting to be brought back together. What if particles aren't particles at all? What if the electron, the quark, the photon, everything we call fundamental is not a point, but a string, a tiny vibrating loop of energy impossibly small, dancing at frequencies that determine what it is and how it behaves? This is the central idea of string theory, and it might be the answer to everything we've been searching for, or it might be the most beautiful mistake physics has ever made. Either way, it changes what reality means at the Planck scale. The year was 1968. Physicists were trying to understand the strong nuclear force, the glue that holds atomic nuclei together. Experiments were producing dozens of new particles, and no one understood the pattern. The mathematical zoo was getting crowded. A young Italian physicist named Gabriele Veneziano was searching through old mathematics papers, looking for a formula that might describe the behavior of these particles. And he found something unexpected. A formula from the 19th century Euler's beta function seemed to match the experimental data perfectly. But why? What did this old mathematical function have to do with subatomic particles? It took a few years to figure out. In 1973, physicists working independently, Yoichiro Nambu Holger Nielsen and Leonard Susskind, realized what Veneziano's formula was describing. It was the quantum behavior of a vibrating string, not particles, strings. The idea was strange, but it worked mathematically. A tiny one-dimensional string could vibrate in different modes, like a violin string playing different notes. Each vibrational mode would appear as a different particle. The energy of the vibration would determine the particle's mass. The pattern of the vibration would determine its quantum properties. It was elegant, beautiful, and completely wrong for describing the strong force. By the mid-70s quantum chromodynamics, a different theory had successfully explained the strong force. String theory seemed like a dead end. Most physicists abandoned it, but a few stayed because they noticed something extraordinary hidden in the equations. One of the vibrational modes of a closed string, a loop with no ends, corresponded to a massless spin 2 particle. And there's only one particle in nature with those properties, the graviton, the hypothetical quantum particle that carries the gravitational force. String theory naturally included gravity. It didn't need to be added. It emerged automatically from the mathematics. This was unprecedented. Every other attempt to create a quantum theory of gravity had failed. But here was a theory where gravity just appeared uninvited but welcome. Scientists began to see string theory differently, not as a theory of the strong force, but as a theory of everything, a framework that could describe all particles and all forces in a single unified way. And the key scale, the natural length scale of these strings, was the Planck length. Let's understand what a string is, or rather what string theory says a string is. A string is not made of anything. It's not a material object. It's a fundamental excitation of space-time itself, the smallest possible wiggle, a one-dimensional curve about 10 to the negative 35 meters long, existing in 10 or 11 dimensions. Yes, extra dimensions. String theory requires them. In our everyday experience, we see 3 dimensions of space and 1 of time. But string theory suggests there are 6 or 7 more spatial dimensions curled up so tightly that we can't perceive them. Their size, about the Planck length. These extra dimensions aren't just mathematical tricks. They're essential to the theory's consistency. Without them, string theory produces anomalies, mathematical inconsistencies that make the theory nonsensical. But with exactly 10 or 11 dimensions, the anomalies cancel. The theory works. So why don't we see these extra dimensions? Because they're compactified, rolled up into tiny shapes, Calabi-Yau, manifolds in the technical jargon so small that even our most powerful particle accelerators can't probe them. Imagine an ant walking on a garden hose. From far away, the hose looks one-dimensional, just a line. But up close, the ant sees that the hose has a circular cross-section. There's an extra dimension curled around the main axis. String theory suggests that every point in our 3-dimensional space has extra dimensions curled up at the Planck scale. We're like observers too large to see them. Now these strings can be open or closed. Open strings have 2 ends. Closed strings are loops, and they can vibrate in countless ways. Think of a guitar string. Pluck it, and it vibrates at a fundamental frequency. But it also vibrates at higher harmonics multiples of that fundamental frequency. Each harmonic is a different mode of vibration. String theory strings are similar. Each mode corresponds to a particle. The lowest mode of an open string might be a photon. A higher mode might be an electron. An even higher mode might be some exotic particle we haven't discovered yet. For closed strings, one of the modes is the graviton. This is what makes string theory special. Gravity emerges naturally. It's not added by hand. It's a consequence of the string's ability to close on itself and vibrate. The mass of each particle is determined by the vibrational energy. Higher frequency vibrations have more energy and therefore more mass via Einstein's E equals mc squared. The massless particles, photons, gluons, gravitons, correspond to the lowest energy modes. The massive particles, electrons, quarks W and Z bosons, correspond to higher modes. It's as if the universe is a symphony. Each particle is a note, and the strings are the instruments playing them. But here's the crucial part. The strings are Planck length-sized. They're as small as physically meaningful distances can be. This gives string theory a natural cutoff, a way to avoid the infinities that plague other attempts to quantize gravity. Remember the problem with point particles. When you try to calculate their interactions, you have to integrate over all possible distances, including infinitely small ones. And those integrals diverge. You get infinite answers. But strings have a finite size. They're not points. They're extended objects about a Planck length long. When two strings interact, when they merge or split, the process is smeared out over this finite size. There are no point-like singularities, no infinitely small distances, no divergences. The infinities that destroy quantum gravity vanish in string theory, or rather, they never appear in the first place. The theory is ultraviolet finite, as physicists say. It makes sense at arbitrarily high energies. This is why many physicists believe string theory is the right path toward quantum gravity. Not because it's been experimentally confirmed it hasn't, but because it's the only known theory that naturally includes gravity without breaking down at the Planck scale. Now, string theory didn't just produce one version, it produced five. 5 different string theories, each with its own rules, its own particle content, its own mathematical structure. They're called Type 1, Type YIA, Type YIB, Heterotic, SO32, and Heterotic E8X, E8. For a while, this was confusing. If string theory is the theory of everything, why are there 5 versions? Which one describes our universe? And then in 1995, Edward Witten made a breakthrough. He showed that the 5 theories are not separate. They're different perspectives on a single underlying theory. Different ways of looking at the same thing. He called this deeper theory M theory. No one knows what the M stands for. Some say membrane, because the theory includes not just strings, but higher dimensional objects called brains. Others say mystery because we still don't fully understand it. Witten himself has said it stands for magic's matrix, or mother of all theories. M theory lives in 11 dimensions. The 5 string theories emerge as special limits of M theory, different slices through the 11-dimensional space. It's as if you're looking at a 3-dimensional sculpture from different angles, and each angle looks like a different 2-dimensional picture. But there's only one sculpture. This unification was profound. It suggested that there's a unique theory at the deepest level, that the apparent multiplicity is just a matter of perspective. That string theory is not just a candidate for the theory of everything but the candidate. And yet, M theory remains incomplete. We don't have the full equations. We have pieces, glimpses, approximations. But the complete formulation, the one that would tell us exactly what happens at the Planck scale, eludes us. Still, string theory has made remarkable predictions, or rather postdictions. In 1996, Andrew Strominger and Kumrun Vafa used string theory to calculate the entropy of certain black holes. Entropy is a measure of disorder, of the number of possible internal states of a system. For black holes, Stephen Hawking and Jacob Bekenstein had derived a formula in the 70s. The entropy is proportional to the area of the event horizon. but no one knew why. Why area? Why not volume? What are the internal states of a black hole? Strominger and Waffe answered this using D-Brain's special objects in string theory that strings can attach to. They showed that a black hole could be modeled as a collection of D-brains, and by counting the quantum states of the strings attached to these brains, they reproduced the Bekenstein-Hawking formula exactly. This was stunning. It was the first time anyone had derived black hole thermodynamics from a fundamental theory. It suggested that string theory really does describe quantum gravity, that it really knows what's happening at the Planck scale. But there's a problem, a big problem. String theory has no testable predictions at accessible energies. The natural energy scale of string theory is the Planck energy 10 to the 19 giga-electron volts. That's 1,000,000 trillion times higher than the Large Hadron Collider can reach. It's beyond anything we can build with foreseeable technology. At lower energies, the energies we can probe, string theory looks like ordinary quantum field theory. The strings are so small, vibrating so fast that they appear as point particles. All the exotic effects, all the extra dimensions, all the quantum gravity phenomena, they're hidden, invisible. This has led to criticism. Some physicists argue that string theory is not science because it can't be tested, that it's beautiful mathematics perhaps, but not physics, that without experimental confirmation, it's just speculation. Defenders of string theory respond that this is unfair, that many theories in the history of science were not immediately testable, that the mathematics is so compelling, so consistent, so rich, that it must be telling us something true about nature. And they point to indirect tests, to the hope that the extra dimensions might leave subtle imprints on particle physics. That supersymmetry asymmetry predicted by string theory might be discovered at the next generation of colliders, that gravitational waves or cosmic rays or astrophysical observations might reveal Planck scale effects. So far, none of these hopes have materialized. Supersymmetry has not been found. The extra dimensions remain hidden. The Planck scale stays out of reach. But string theorists continue, because the theory is too beautiful to abandon, too elegant, too close to what a unified theory should be. Consider what it offers: a single type of object, the string that can account for all particles and all forces, a natural explanation for why gravity exists, a resolution of the infinities that plagued quantum gravity, a framework that includes both quantum mechanics and general relativity without contradiction. It's not complete, it's not proven, but it's the best answer we have to the question, what is reality at the Planck scale? And the answer it gives is, this reality is music, vibrations, harmonics. The universe is a symphony played by strings too small to see in dimensions too curled to perceive, at frequencies too high to hear. Every particle is a note, every force is a chord, and the laws of physics are the score. It's a poetic vision. Whether it's true remains to be seen. But it's hard not to be moved by it, by the idea that at the deepest level, matter is not solid but singing, that the fundamental building blocks of reality are not bricks but songs. Planck found the scale. Wheeler imagined the foam. And string theory suggests that within that foam, at that scale, tiny loops of energy are dancing, spinning, vibrating, creating the illusion of particles, the illusion of forces, the illusion of the space-time stage itself. If string theory is right, then when you zoom into the Planck scale, you don't find smaller particles, you find strings. And when you zoom into strings, you find nothing. Because strings are fundamental. They're not made of anything smaller. They're the bottom level, the ground floor of reality. Or maybe not. Maybe strings themselves emerge from something deeper. Maybe M theory has layers we haven't discovered yet. Maybe the Planck scale is not the end but a way station, a door to even stranger territories. We don't know, not yet, but we're listening. Listening for the music, for the vibrations, for the strings that might be singing the universe into existence one Planck-length loop at a time. There was a moment, a single impossible moment, when the entire universe was smaller than the period at the end of this sentence. When everything that would become galaxies and stars and planets and you was compressed into a region tinier than the Planck length. When time itself had not yet learned how to flow. This moment is called the Planck epoch, and it is the most mysterious instant in all of cosmic history. We cannot see it, cannot calculate it, cannot even speak about it with confidence. But it happened, and everything we are traces back to that infinitesimal flash. The story begins with a Belgian priest named Georges Lemaitre. In 1927, he proposed something radical: the universe is expanding. If you run time backward, he reasoned all the galaxies would converge, space would shrink, everything would compress into what he called the primeval atom, a single point from which the universe exploded. Most physicists dismissed him. The idea seemed absurd, religious even, a creation moment in physics. But in 1929, Edwin Hubble made a discovery. He measured the light from distant galaxies and found that they were all moving away from us. The farther the galaxy, the faster it receded. The universe was expanding exactly as Lemaitre had predicted. This changed everything. If the universe is expanding now, it must have been smaller in the past, denser, hotter. Follow that logic far enough, and you reach a beginning. A moment when the universe was infinitely dense, infinitely hot, infinitely small. This became known as the Big Bang, not an explosion in space, but an explosion of space, the birth of everything. And when scientists tried to calculate what happened in the first moments after that birth, they found themselves at the Planck scale. Let's trace the timeline. Let's count backward from the present toward the beginning and see where physics takes us. Today, the universe is about 13.8 billion years old. Vast, cold, mostly empty. Galaxies are separated by millions of light years. Stars are scattered through the dark. The average temperature of space is about 3 Kelvin, just above absolute zero. But 1 billion years after the Big Bang, the universe was smaller, denser, hotter. About 3,000 Kelvin on average. This is when the first stars formed, when light could finally travel freely through space. Go back further. 380,000 years after the Big Bang. The universe was even smaller, even denser, even hotter. About 3,000 Kelvin everywhere. This is the moment of recombination, when electrons and protons combine to form neutral hydrogen. Before this, the universe was a plasma, a hot soup of charged particles that scattered light in all directions. You couldn't see through it. It was opaque. This is as far back as we can see directly. The cosmic microwave background, the oldest light in the universe, comes from this moment. It's our visual horizon, the edge of the observable past. But physics lets us go further, much further. 1 second after the Big Bang, the temperature was about 10 billion Kelvin, hot enough that atomic nuclei couldn't form yet. The universe was a sea of protons, neutrons, electrons, and photons all colliding wildly. 1 millisecond after the Big Bang, the temperature was 1 trillion Kelvin. Quarks and gluons had just begun to bind together to form protons and neutrons. Before this, they existed freely in a quark-gluon plasma, a state of matter so extreme that we've only barely recreated it in particle colliders. 1 microsecond after the Big Bang, the temperature was 10 trillion Kelvin. The weak and electromagnetic forces which are unified at high energies were just beginning to separate. 1 nanosecond after the Big Bang, 1 billionth of a second, the temperature was 10 quadrillion Kelvin. This is about as hot as the Large Hadron Collider can recreate. Beyond this, we're in territory that has never been experimentally probed. We're relying purely on theory, on extrapolation, on educated guesses about how physics behaves at energies we've never reached. But we can keep going. The equations still make sense, at least for a while. 1 trillionth of a second after the Big Bang, the temperature was about 10 to the 16th Kelvin. This is roughly the energy scale of grand unification, where the electromagnetic weak and strong forces merge into one. At this moment, there were only two forces in the universe, gravity and the grand unified force. And we're still not at the beginning. 1/10 trillionth of a second after the Big Bang, we reach the Planck temperature, 10 to the 32 Kelvin. This is as hot as anything can be. It's the point where the thermal energy of particles equals the Planck energy, where quantum gravity effects dominate, where space-time itself becomes uncertain. And before this, in the time between 0 and 10 to the negative 43 seconds, in the Planck epoch, we don't know. Our theories break down. General relativity predicts a singularity, a point of infinite density and infinite curvature. But we know this can't be right. Infinities in physics are usually signs that the theory is being pushed beyond its limits. Quantum mechanics should become important at these scales. But we don't have a quantum theory of gravity that works, so we can't calculate what actually happened. We can only speculate. Some researchers suggest that space-time itself did not exist during the Planck epoch, that it emerged crystallized in a sense as the universe cooled and expanded, that before space-time, there was something else, something more fundamental, perhaps a quantum state, perhaps a network of quantum loops, perhaps vibrating strings in higher dimensions. Others propose that time itself is meaningless at the Planck scale, that asking, what happened before the Planck epoch, is like asking, what's north of the North Pole? The question doesn't make sense because time as we understand it only exists after the Planck epoch. Still others suggest that the universe never was infinitely small, that quantum effects, perhaps a kind of quantum pressure, prevented the full collapse to a singularity, that the Big Bang might have been a big bounce where a previous universe collapsed to Planck-scale densities and then rebounded, creating our universe. We don't know which, if any, of these ideas is correct. The Planck epoch is beyond our current reach. It's the ultimate frontier, the place where all our theories point and then fall silent. But let's imagine it anyway. Let's picture what the universe might have been like in that first impossible moment. The entire observable universe, everything we can see with our telescopes, all 100 billion galaxies, all the vast stretches of space between them, was compressed into a region smaller than a single proton. Actually, much smaller, about the Planck length, 10 to the negative 35 meters. The temperature was the Planck temperature, 10 to the 32 Kelvin, so hot that particles moved at nearly the speed of light, so hot that the distinction between matter and energy blurred completely, so hot that space-time itself fluctuated wildly, losing its smooth structure. At this temperature, at this density, all four fundamental forces were unified. There was no separate gravity, no separate strong force, no separate electro-weak force. Just one force, one interaction, the superforce that governed everything, and time. Time barely existed. Each moment lasted only a Planck, time 10 to the negative 43 seconds. And in that unimaginably brief span, the universe changed completely. Space expanded. Energy transformed. The unified force began to split apart. First, gravity separated. It became distinct from the other forces. This happened at the end of the Planck epoch, as the universe cooled from the Planck temperature to slightly lower energies. Scientists estimate this happened at about 10 to the negative 43 seconds after the beginning. Then, around 10 to the negative 36 seconds, the strong force split off from the electro-weak force. Grand unification ended. Now there were three forces: gravity, the strong force, and the electro-weak force. And shortly after, perhaps at 10 to the negative 12 seconds, the electromagnetic and weak forces separated. The four forces we know today were now distinct. But all of this entire cosmic drama began in the Planck epoch. In that first singular flash when the universe was as small and as hot as anything can be. Now here's something profound. During the Planck epoch, quantum effects dominated. The universe was so small that it was in essence a quantum object. Not a classical deterministic system, but a probabilistic, uncertain, fluctuating something that we can barely conceptualize. What does it mean for the entire universe to be quantum? What does it mean for space-time itself to be in a superposition of states? What does it mean for causality, cause, and effect to be undefined? These questions don't have answers yet, but they haunt cosmology. They suggest that the beginning of the universe was not a point in time and space, but something stranger, something outside our usual frameworks. Some cosmologists propose that the universe began in a quantum fluctuation of the vacuum, that it tunneled into existence from nothing, or from something, a quantum foam perhaps, that predated space and time. Others suggest that the Planck epoch was the moment when the wave function of the universe collapsed, when quantum possibilities became classical actualities. Though what caused the collapse, or whether collapse even makes sense in this context, is deeply unclear. Still others embrace the many worlds interpretation of quantum mechanics and suggest that the Big Bang created not one universe, but infinitely many, every quantum possibility realized in a different branch of the wave function. An infinite multiverse, all born in that single Planck scale moment. These ideas are speculative, untestable perhaps. But they're what happens when you follow the logic of quantum mechanics and cosmology to their ultimate conclusion. When you ask what the universe was like at the Planck scale, and then there's inflation, Alan Guth's brilliant insight from 1981. He proposed that shortly after the Planck epoch at around 10 to the negative 36 seconds, the universe underwent a period of exponential expansion. In a tiny fraction of a second, space doubled in size, then doubled again, then again, over and over, at least 60 times. This inflation solved several problems in cosmology. It explained why the universe is so uniform, so flat, so homogeneous. But it also amplified quantum fluctuations. Tiny ripples in the quantum fields during inflation were stretched to cosmic scales, becoming the seeds of galaxies. Those ripples quantum uncertainty made manifest are still visible today in the cosmic microwave background, in the slight temperature variations across the sky, in the pattern of galaxies and voids. The quantum randomness of the Planck epoch echoes through the cosmos, visible 13 billion years later. It's extraordinary. The largest structures in the universe, superclusters of galaxies' cosmic filaments. The great voids all trace back to quantum fluctuations when the universe was Planck scale. The smallest physics determines the largest structures. And here's the humbling part. We will never see the Planck epoch directly. It's hidden behind a veil, not a veil in space, but a veil in time. A horizon beyond which no light, no signal, no information can reach us. The cosmic microwave background is our earliest light, but it comes from 380,000 years after the Big Bang. Everything before that is opaque, and the Planck epoch is 10 to the 38 times earlier than that. We can calculate, we can theorize, we can imagine, but we cannot observe. The Planck epoch is a cosmic horizon forever beyond our direct view. And yet, it's where we came from. Every atom in your body, every photon that enters your eyes, every force that holds you together, all of it emerged from that moment, from the Planck epoch, from the instant when the universe was smaller than small and hotter than hot and stranger than strange. Do you ever wonder what it felt like, if felt even makes sense? To be present at the beginning, to exist in a universe that was entirely quantum, where space-time was not a stage but a participant fluctuating wildly uncertain of its own geometry. We can't know. But we can stand here 13.8 billion years later in a cold, vast, ancient universe and look back. We can trace the thread of cosmic history all the way to that first moment. We can see how the universe cooled, expanded, evolved, how forces separated particles, formed atoms, assembled stars, ignited galaxies, gathered planets, coalesced, life emerged. And we can realize that all of it, every bit of it, began at the Planck scale. In a moment so brief, so small, so intense that our languages fail, Our intuitions collapse and our theories stand at the edge and whisper, here is where everything begins, and here is where we must learn to imagine differently. Imagine a black hole the size of a proton, actually much smaller, the size of the Planck length. It would have a mass about 22 micrograms, roughly the weight of a flea's egg, and it would exist for less than a heartbeat, less than a blink, less than the briefest moment you could imagine. And then, in a flash brighter than a supernova, it would evaporate. These are quantum black holes, the smallest black holes that can possibly exist. And they live at the boundary where Einstein's gravity meets Heisenberg's uncertainty, where mass becomes so compressed that space-time itself screams. They might be the keys to everything. The story begins in 1915, when Carl Schwarzschild solved Einstein's equations. He found something unexpected, a prediction of objects so dense that nothing, not even light, could escape them. At the time, no one believed they were real. Einstein himself thought nature would prevent such extremes. But Schwarzschild's mathematics was clear. If you compress enough mass into a small enough region, you create an event horizon, a surface of no return. Cross it, and you can never come back. Space itself flows inward faster than light can travel outward. The critical size is called the Schwarzschild radius. For the Sun, it's about 3 kilometers. Compress the Sun into a sphere 3 kilometers across, and it becomes a black hole. For Earth, the Schwarzschild radius is about 9 millimeters. For you, for a typical human, it's about 10 to the negative 25 meters. Far, far smaller than an atom. The formula is simple. The Schwarzschild radius equals 2 times the mass, times Newton's gravitational constant divided by the speed of light squared. It's a direct relationship. More mass means a larger black hole, less mass means a smaller one. But there's a limit, a smallest possible black hole, and it occurs exactly at the Planck scale. When the mass equals the Planck mass, about 22 micrograms, the Schwarzschild radius equals the Planck length, about 10 to the negative 35 meters. This is the quantum black hole, the point where gravity and quantum mechanics collide with full force. Why is this the smallest? Because of Heisenberg's uncertainty principle. Remember, to confine something to a region, the size of the Planck length requires enormous momentum, enormous energy, and energy is equivalent to mass. So, when you try to create something smaller than a Planck-length black hole, the energy you need to confine it is so high that it creates a larger black hole instead. It's a cosmic catch-22. You can't make black holes smaller than the Planck scale because the act of trying creates bigger ones. The Planck length is not just the smallest meaningful distance, it's the smallest black hole that can exist. But these tiny black holes don't last. They evaporate. This was Stephen Hawking's great discovery in 1974. He showed that black holes are not completely black. They emit radiation. They glow very faintly with thermal radiation, at a temperature inversely proportional to their mass. Large black holes' stellar mass, supermassive, are cold, colder than the cosmic microwave background. They absorb more energy from the universe than they emit. They grow. But small black holes are hot, very hot. And the smaller they are, the hotter they get. A black hole with the mass of the Sun would have a temperature of about 60 nanokelvins, barely above absolute zero. It would take 10 to the 67 years to evaporate far longer than the current age of the universe. But a Planck mass black hole has a temperature of 10 to the 32 Kelvin, the Planck temperature, the hottest possible temperature, and it evaporates in about 1 Planck time, 10 to the negative 43 seconds. It's born and it dies in the briefest instant physics allows. A flash of pure energy, a quantum hiccup in space-time. Why do black holes evaporate? It's connected to the vacuum fluctuations we discussed earlier. Near the event horizon of a black hole, virtual particle pairs are constantly forming. Normally, they annihilate back into nothing. But near a black hole, something different can happen. One particle of the pair can fall into the black hole while the other escapes. To an outside observer, it looks like the black hole emitted a particle. But where did the energy come from? From the black hole's mass. The escaping particle carries away energy and the black hole shrinks. This process is called Hawking radiation. And it's irreversible. Once it starts, the black hole continues to lose mass. As it shrinks, it gets hotter. As it gets hotter, it evaporates faster. The process accelerates running away until in the final moments, the black hole explodes in a burst of high-energy radiation. For a Planck mass black hole, this entire process from formation to evaporation takes one Planck time. It's the ultimate ephemeral object, a ghost in the quantum foam. But here's what makes quantum black holes fascinating. They might be everywhere, constantly forming and evaporating in the quantum vacuum. Wheeler's space-time foam, remember, is a churning sea of quantum fluctuations. Energy fluctuates. And where energy concentrates, it curves space-time. If enough energy fluctuates into a small enough region, a region about the Planck length across it could form a tiny black hole. These would be virtual black holes, not real in the classical sense, but quantum mechanically real, popping in and out of existence, contributing to the texture of space-time at the smallest scales. Some physicists believe these virtual black holes are what makes space-time discrete, that they're the fundamental pixels of reality, each one a tiny knot in the fabric, existing for a Planck time before dissolving. Others suggest that they might solve the cosmological constant problem, that their energy, their contribution to the vacuum energy, might cancel in some clever way we haven't understood yet. Still others wonder if there are the building blocks of larger black holes, if stellar mass black holes and supermassive black holes are in some sense made of countless quantum black holes bound together. We don't know. But the mathematics points in interesting directions. Now, let's talk about black hole entropy. This is where things get truly strange. In the 1970s, Jacob Bekenstein and Stephen Hawking derived a formula for the entropy of a black hole. Entropy measures disorder, the number of ways a system can be arranged internally, while looking the same externally. For most objects, entropy is proportional to volume. More space means more ways to arrange things. But for black holes, entropy is proportional to area, specifically to the surface area of the event horizon. In Planck units, the entropy equals 1/4 the area of the horizon. This was shocking. Why area? Why not volume? What are the internal states of a black hole? No one knew. The formula was correct. It matched thermodynamic calculations perfectly, but its physical meaning was obscure. Then string theory entered, and in 1996, Andrew Strominger and Kumran Vafa did something remarkable. They took a special class of black holes, extremal black holes, which have charge equal to their mass, and modeled them using D-branes in string theory. D-branes are objects that strings can stick to. They're like surfaces embedded in higher dimensional space. Strominger and Vafa showed that you could build a black hole by stacking D-branes on top of each other. And then they counted the quantum states of the strings attached to these branes. The number they got matched the Bekenstein-Hawking entropy exactly. This was stunning. For the first time, someone had derived black hole entropy from a microscopic theory. They had counted the actual states, the internal configurations, the degrees of freedom that make up a black hole's entropy. It was like finally understanding why a gas has entropy. Because it's made of molecules, and there are many ways to arrange those molecules. A black hole, according to string theory, is made of strings and branes, and there are many ways to arrange those strings and branes. The area law entropy proportional to area emerges naturally from this counting. It's a consequence of the holographic nature of quantum gravity. The idea that all the information in a three-dimensional volume is somehow encoded on its two-dimensional boundary. This holographic principle, as it's called, suggests that space-time is not fundamental, that it's a projection, an emergent phenomenon arising from quantum entanglement, or information, or something even more basic. and quantum black holes might be the clearest example of this. They're the points where space-time is most compressed, most extreme, most quantum. They're where the holographic nature of reality becomes undeniable. But there's a paradox, a deep unresolved paradox, the information paradox. When something falls into a black hole, it carries information. The arrangement of its atoms, the state of its quantum fields, its history. According to classical general relativity, that information is lost. It crosses the event horizon and is gone forever unreachable from the outside. But quantum mechanics says information cannot be destroyed. It can be scrambled, hidden, encrypted, but never truly lost. The universe must preserve information. It's a fundamental principle. So, what happens to the information that falls into a black hole? Does it survive? Does the black hole encode it on its event horizon, as the holographic principle suggests? Or does it escape somehow, when the black hole evaporates through Hawking radiation? Hawking himself initially believed the information was lost. That black hole evaporation was genuinely random, with no correlation to what fell in. But later, he changed his mind. He came to believe that information must escape, though how it escapes remained unclear. String theory offers hints. It suggests that black hole evaporation is not random, that the radiation carries subtle correlations imperceptible to classical observers, but there nonetheless. That the information is encoded in quantum entanglement between the emitted particles, but the details are murky. We don't have a complete picture. The information paradox remains one of the deepest puzzles in theoretical physics. And quantum black holes are at the heart of it, because they evaporate completely. There's no remnant left. All the mass converts to radiation. If information is to survive, it must be in that radiation. But Hawking radiation appears thermal, random, featureless. Where is the information hiding? Some propose that the final burst, the last moment of evaporation, carries all the information out in a concentrated pulse. Others suggest that the information never enters the black hole at all, that it's reflected at the event horizon in a way too subtle for us to detect. Still others embrace the many worlds interpretation and say the information survives in other branches of the quantum wave function. These are not idle speculations. They're attempts to reconcile quantum mechanics and gravity, to understand what really happens at the Planck scale, to decode the messages that quantum black holes might be sending us. And here's a wild thought. Maybe quantum black holes are portals, tiny wormholes connecting distant points in space or distant moments in time. Shortcuts through the fabric of space-time, opening and closing in Planck time intervals. Einstein and Nathan Rosen proposed this in 1935. They showed that the mathematics of black holes admits solutions where two black holes, one here, one there, are connected by a bridge, a tunnel through space-time. An Einstein-Rosen bridge, later called a wormhole. For large black holes, these wormholes are unstable. They collapse before anything can pass through. But for quantum black holes, maybe the rules are different. Maybe in the quantum foam, wormholes are constantly opening and closing, connecting Planck-scale regions of space. If true, this would mean space-time is not simply connected. It's not a smooth manifold. It's riddled with tunnels, with shortcuts, with connections between distant points. At large scales, we don't notice. But at the Planck scale, space might have an incredibly complex topology. This is speculative. But it's consistent with Wheeler's foam, with the idea that space-time at the smallest scales is wild, turbulent, alive, with structure. And quantum black holes are the actors in this drama, the transient, flickering entities that weave the foam together, that create its texture, its randomness, its quantum nature. So, when you think about black holes, don't just think about the massive ones, the stellar remnants, the supermassive monsters at galactic centers. Think also about the tiny ones, the Planck mass ones, the quantum ones. They exist for less than a blink. They're smaller than anything we can measure. They might never be directly observed, but they're there in the mathematics, in the logic of combining gravity and quantum mechanics. in the structure of space-time at its deepest level, and they whisper secrets about information, about entropy, about the holographic nature of reality, about how the smallest things can contain the deepest truths, about how mass, when compressed to its ultimate limit, doesn't just curve space-time, it tears it, twists it, quantum fluctuates it into something we're only beginning to understand. We've traveled far tonight, from a ruler that stops measuring to a universe that began smaller than thought, from smooth space-time that fractures into foam to forces that refuse to unite, from strings singing reality into being to black holes flickering in and out of existence. All of it, every strange idea, every impossible scale, every boundary where physics trembles converges at one place. The Planck scale, 10 to the negative 35 meters, 10 to the negative 43 seconds, the edge of knowledge itself. And here at the end of our journey, we face a humbling truth: we don't know what happens there. Not really, not yet. Let's be honest about what we've discovered and what we haven't. The Planck scale is not proven. It's not observed. It's predicted, calculated, inferred from the mathematics of combining three constants: the speed of light, the gravitational constant, and Planck's quantum constant. When you weave those three together, they point to a scale, a boundary, a place where something changes. But is it real? Is nature actually discrete at the Planck length? Does space-time actually foam? Do strings actually vibrate? Do quantum black holes actually form and evaporate in the vacuum? Or is the Planck scale just an artifact of our current theories, a symptom of their incompleteness, a mathematical mirage that will dissolve when we find the right framework? Scientists argue about this passionately. Some believe the Planck scale is fundamental, written into the fabric of reality by nature herself. Others think it's provisional, a placeholder, until we develop better theories. In 2007, a philosopher of physics named Fabio Meschini published a paper titled "The Planck Scale, Humble Belief or Established Fact." He argued that our confidence in Planck scale physics rests on several uncritical assumptions, that we've been too quick to assume the Planck length marks a real physical boundary. More recently, in 2025, philosopher Caspar Jacobs extended this critique. He examined 5 different arguments for why quantum gravity should become important at the Planck scale: dimensional analysis, quantum black holes, generalized uncertainty principles, the non-renormalizability of gravity, and predictions from theories beyond the Standard Model. His conclusion: none of them are fully convincing. Each relies on assumptions that might not hold. The evidence for quantum gravity at the Planck scale, he argues, relies on heuristics more than on proof. This doesn't mean the Planck scale is wrong. It means we should approach it with humility, with caution, with the recognition that we might be mistaken. And that's okay. That's how science works. We build the best theories we can with the tools we have. We follow the mathematics where it leads, we make predictions, and then we test them. The problem is we can't test the Planck scale, not directly, not with any technology we can currently envision. To probe the Planck length, you'd need a particle accelerator the size of the Milky Way galaxy. To observe Planck time events, you'd need detectors sensitive beyond anything we can build. To create Planck scale energies in a laboratory would require more power than all the stars in the observable universe produce. It's not just difficult, it's practically impossible. The Planck scale might be forever beyond our experimental reach. And yet, scientists haven't given up. They're clever, creative. They look for indirect evidence, for subtle effects, for windows into the Planck regime that don't require impossible energies. One approach uses gravitational waves, those ripples in space-time detected by LIGO and Virgo. Some theories predict that Planck-scale quantum effects might leave tiny imprints on gravitational waves, tiny deviations from Einstein's predictions. Scientists are analyzing the data, searching for these signatures. So far, nothing definitive, but the search continues. Another approach uses high-energy cosmic rays, particles from space that strike Earth's atmosphere with energies far beyond anything our colliders can produce. If space-time is grainy at the Planck scale, these particles might scatter slightly as they travel, blurring their arrival directions. Experiments are looking. So far, the evidence suggests space-time is smooth down to scales much smaller than expected. A third approach uses atom interferometers, incredibly precise devices that measure the quantum states of atoms. Some researchers, including Chuan-Ting Wang and colleagues, have proposed sending atom interferometers into space. There, free from Earth's vibrations and gravitational noise, they might be sensitive enough to detect Planck-scale fluctuations in space-time. The decoherence of quantum matter waves could reveal the hidden foam. These experiments are ongoing. Some are flying, some are planned, some are still dreams waiting for funding. But they share a common hope that the Planck scale, though distant, is not entirely unreachable, that nature leaves clues, that we're clever enough to find them. And even if we can't probe the Planck scale directly, we can still learn from it, because it teaches us about limits, about boundaries, about the edges of knowledge. The Planck scale is not just a physical boundary, it's an epistemological one, a place where our concepts stop working, where distance and duration lose their sharpness, where cause and effect blur, where the questions we're used to asking, what happened, when, where, stop having clear answers. This is uncomfortable. Humans like certainty. We like to believe that with enough effort, enough intelligence, enough time, we can understand everything, that there are no fundamental mysteries, only unsolved puzzles. But the Planck scale suggests otherwise. It suggests that there might be limits to what we can know, not because we're not smart enough, but because the universe is structured in a way that hides certain truths from us. Maybe space-time is emergent. Maybe it's not fundamental. Maybe asking what happens at the Planck scale is like asking, what are thoughts made of? The question presupposes a framework, space-time in this case, that might not apply at that level. Maybe the right question isn't, what is space-time at the Planck scale, but what is the thing from which space-time emerges? What are the fundamental ingredients? What is more basic than space and time? We don't know, but asking the question is progress. Recognizing our ignorance is the first step toward wisdom. And here's something beautiful, something worth holding on to. The Planck scale connects everything. It connects quantum mechanics to gravity. It connects the early universe to black holes. It connects the smallest lengths to the largest energies. It connects the fastest time scales to the hottest temperatures. It's the meeting point, the crossroads, the place where all of fundamental physics intersects. And in that intersection, we glimpse unity. We see hints that the four forces might be one, that particles might be modes of strings, that space-time might be woven from quantum threads, that the universe at its deepest level might be simpler than we thought. Not simpler in the sense of easy to understand, but simpler in the sense of unified, connected, coherent, built from a small number of principles that manifest in rich, complex, surprising ways. This is the dream that drives theoretical physics, the dream of unification, of finding the theory of everything, the single framework that explains all particles, all forces, all of space-time, from the Planck scale to the cosmic scale. We're not there yet. String theory is incomplete. Loop quantum gravity has unsolved problems. Other approaches, causal set theory, asymptotic safety, emergent gravity, are still being developed. None of them are proven. None of them make testable predictions we can verify. But the search continues, because the Planck scale demands it, because the universe has shown us a door, and we cannot help but wonder what's behind it. Max Planck found that door in 1899. He was studying black-body radiation, the glow of hot objects. He had no idea he was discovering the smallest meaningful scale in physics. He thought he was just solving a practical problem. John Wheeler imagined the foam in 1955. He was trying to understand what happens when quantum mechanics meets gravity. He pictured space-time as turbulent bubbling alive. He gave us a metaphor that still shapes how we think. Stephen Hawking showed that black holes evaporate in 1974. He unified quantum mechanics, thermodynamics, and gravity in a single calculation. He revealed that even black holes, the most extreme objects in classical physics, obey quantum rules, and countless others, Einstein, Heisenberg, Nambu, Witten, Strominger, Vafa, and so many more have added pieces to the puzzle, slowly, patiently building our understanding of the Planck scale, brick by mathematical brick. They didn't do it for fame, or money, or certainty. They did it because they were curious, because they looked at the universe and asked, how does it work? What are the rules? What happens at the edges? And they followed those questions into strange territories, into mathematics that twisted their intuitions, into predictions that couldn't be tested, into ideas that seemed absurd. They persisted because the questions mattered, because understanding matters, because we are curious beings, and curiosity is what makes us human. So, where are we now? What do we know? We know there's a scale, the Planck scale, where our current physics breaks down, where general relativity and quantum mechanics, separately successful, cannot both be true, where something new must happen, something we haven't discovered yet. We know this scale is unimaginably small and unimaginably energetic, far beyond our direct reach, perhaps forever beyond it. We know that understanding this scale would unlock profound secrets, the nature of space-time, the origin of the universe, the fate of information in black holes, the unification of forces, maybe even the reason why there is something rather than nothing. And we know we don't have the answers, not yet. Maybe not for a long time, maybe ever, but we're looking, we're calculating, we're imagining. We're building theories and testing them against mathematics and logic and the indirect clues nature provides. We're inching closer, one insight at a time, toward the Planck scale's secrets. And even if we never reach it, even if it remains forever out of reach, the journey matters. The attempt matters. The questions we ask and the frameworks we build and the beauty we find in the mathematics, all of it enriches us. All of it expands our understanding. All of it reminds us that the universe is larger and stranger and more wonderful than we imagined. So, rest now. Let these ideas settle. Let them drift through your mind like distant stars. You don't need to grasp them all. You don't need to solve them. Just rest in the wonder, in the mystery, in the recognition that reality at its smallest scales is strange beyond imagining. The Planck scale is a boundary, a horizon, a place where knowledge ends and wonder begins, where physics points and says, here is something I cannot yet describe. Here is something deeper. Here is something waiting, and maybe that's enough. Maybe knowing that there are depths we haven't plumbed, mysteries we haven't solved, questions we haven't asked. Maybe that's what keeps us searching, keeps us curious, keeps us human. Thank you for drifting with me tonight, for following these strange paths into the smallest corners of reality, for holding space for ideas that twist the mind and challenge the imagination, for wondering alongside me about what lies at the Planck scale, that impossible, beautiful, unreachable place where the universe keeps its deepest secrets. There are more stories to tell, more mysteries to explore, more quiet nights to spend wondering about the cosmos. I hope you'll return. I hope you'll keep asking questions, keep seeking, keep marveling at a universe that is at every scale stranger than we can think. Until then, sleep softly, dream deeply, and remember, the smallest things hold the largest mysteries. Good night,